Today is May 9th, so it has been approximately 1 month and 3 days since we created our alum solutions, and this is what my crystals are looking like now. There's definitely some larger ones in here than when I made the last video update. So stuff is happening, but very slowly, which is likely due to the fact that there is a lack of airflow in my apartment. So there is less evaporation than I would like for the crystals to form, but it's still exciting to see a few more crystals in there. To grow a single large crystal of alum, what I would have done differently, as opposed to what we did do, is I would take one of the crystals that I've grown already and fix it to a nylon fishing line or some sort of way to let it hang inside of a jar. And I would hang it in a saturated solution of alum. Just let it hang there. And this crystal would serve as the seed to which ions would be attracted, thus forming one large alum crystal. And this would help at the initial phase of crystal growth. What we started with was just a saturated solution, so that made it more likely for multiple smaller crystals to form. So this would be the way to grow a larger crystal. Crystals are composed of atoms, ions, or molecules arranged in a uniform pattern, forming a crystal lattice that has some sort of symmetry, similar to this terrible drawing here. And the interatomic spacing between parallel planes of atoms in a crystal is called the d spacing. So the parallel planes here are marked, they're highlighted in pink, and the space in between each one of these would be considered the d spacing. D spacing is important because each crystal has a unique structural pattern and thus a unique d spacing value. So through the use of X-ray diffraction, scientists can determine the spacing between atoms or molecules and identify what type of crystal it is, what makes up the crystal, and other properties of the crystal itself. Now, to determine d spacing, experimentally, we would be given a data set that looks something like this. And what we're looking at is a powder X-ray diffraction data set. On the x-axis, it gives us degrees in 2 theta. The y-axis gives intensity, and lambda, or the wavelength of the X-rays, given up here as 0.15418 nanometers, or 1.5418 angstroms. The equation that we use to calculate d-spacing is given by Bragg's law. And Bragg's law states that when a beam of X-rays of wavelength lambda enters a crystal, the maximum intensity of the reflected ray occurs when sine theta equals n lambda over 2d, when theta is the complement of the angle of incidence, n is a whole number, and it's going to be 1 in this case, and d is the distance between layers of atoms. So, to determine d, we simply have to look back at the graph and obtain a few values, and then plug them into the rearranged Bragg's equation, which I rearranged as d equals lambda over 2 sine theta. So looking back at the graph, one thing to point out is that these high intensity peaks, this one being the maximum, but there are multiple in here, that shows a prominent crystal plane. So when we're looking at the graph, we already have lambda, and what we need to see is to look at the maximum peak. That would be right here. We'd look at the x-axis, and I would say that peak occurs at approximately 20.5, give or take, 2 theta. So if 2 theta is equal to 20.5, then we would have theta equal to 10.25. So we would just plug the value of lambda and theta into this equation. So 1.5418 angstroms over 2 sine 10.25. And we would calculate that to get 4.332 angstroms, which would be our d spacing based on the given data set.